this is Professor Thayer, and I'm going to be talking to you today about periodic relations among elements. And I prepared this recording for you because I unfortunately won't be able to be with you in class, so I hope you enjoy the presentation. So this is about Chapter 8. You'll be able to find the slides. I'll post them on Moodle for you. And so we're going to talk about how the elements are related on the periodic table. So, as you have seen already, we have the periodic table, and the periodic table has the elements arranged on it with regard to their electronic configuration. So, for example, in the first column over here, we have the elements that are going to be arranged by the ones which have one electron which is going to get donated, right? So all of these are going to donate one electron, and then these are going to have a positive +1 charge. The ones over here are all going to have a -1 charge because all of these want to get one more electron, and over here we have the noble gases, which all have the configuration of having the outer shell being full. So then that follows throughout the periodic table that all of the ones in the same column are going to have a similar ground state electron configuration. And so this is how they have been grouped in the columns on the periodic table. So for example, these here all have the first D electron being filled, D5, right, and so forth, all the way up to 10. And then these over here are going to be filling in the the P, so we have 6P electrons, and so then these have the similar configuration. So the idea is then that the outer electron configuration is going to be similar, and because the outer electron configuration is similar, also the chemical properties will be the same because the chemical properties are quite similar to the electron configuration, right? So if they have one valence electron, then they're going to react very similarly to something else that has another valence electron. Finally, we have the group down here. These are the lanthanide and actinide series, and these are filling the 4F and the 5F shells. So then, how are the elements going to be classified on the periodic table? Well, these are classified in 6 major categories. First of all, we have what is known as the representative elements, which are these ones in gray. We have the noble gases, which are over here in group 8A. We have the transition metals, which are these ones in here. We have the zinc, cadmium, mercury series, which is this right here. And then we have the lanthanides and actinides, which are these two down here, which are displayed on the periodic table. Just as a note, of course, if we had the periodic table in its actual form, then there would actually be a space in here, and the lanthanide and actinides would actually be inside the periodic table over here, and the table would be much, much wider. And so the reason why we typically write them below is simply because the periodic table would be too wide to be fitting conveniently onto a standard piece of paper. So what we usually do is we just remove them and put them down at the bottom with the understanding that the periodic table actually has that expansion in there. So the cations and anions of the representative elements then are going to form having similar charges. So basically, because the way the periodic table is set up, that means that if you have the similar electron configuration in the outer shell, then they're going to form similar cations and anions in the same column, right? So if you have one extra electron that's unpaired over in the outer shell, and so in order to get the octet that it would donate 1, that means that all of these would donate 1 because they have a similar electron configuration. So these would become the +1s because they donate 1 electron. These would become the +2s. These ones over here become the +3s. Now, as we move over to the more electronegative elements, instead of wanting to give up electrons in order to get an octet, they would instead rather take up electrons. So, for example, this series right here, right, all of these would like to take up 1 more electron. These need 2 more electrons, and these need 3 more electrons to move over to their noble gas configuration, which we can see by walking over here, right? So we need 1 step, 2 steps, and so forth. So, because they, again, are in the same column and they have the same outer electron configuration, then they are going to have very similar charges. And so that's part of why they are grouped together the way they are. Alright, so electron configurations of cations and anions of the representative elements. So here what we're doing is we are showing what the outer electron configuration is. Now, you see how we have these configurations with the noble gases in here. The electron configurations are going to be representative of how the electrons are filling. So if we just step back for a moment, you could fill, so what you'll be doing is you'll be filling the different subshells, right? So this is the S subshell, so we have 1s and 2s. As you move down the periodic table, we'll be filling the shells. So the subshells are going to be S, P, D, and F, and the shells are going to be the rings. So that's like as you move out from the center in the Bohr model, which level of ring you're at. So here we have the first shell, and so this will be the S electrons. Then we'll fill the, these represent filling the 2 electrons in the S. Helium is unique in being over here in that this is the second electron being filled, so we could actually represent helium over here as well, because that would also be filling the second S electron. However, it also means that when it has 2 electrons, it has an outer full shell, so that's why it's over here. Helium is also unique in that its outer shell being full is not an octet, because it only needs 2 to be full. So we usually put it over here because it's most similar to the noble gases because they have the full outer shell. So when we are doing the filling, we actually have the fillings written down in here, which you probably can't read here, but you can read on the copy. You can get off Moodle. You can see that the electron filling configurations then are adding 1 electron as we move from one block to the next. So for example, this has 1 electron, 2 electrons, 3 electrons, and 4 electrons, and so forth. So as we move through the periodic table, we're going to add 1 additional electron. So as I was saying, here we're going to fill the S subshell. This is the P subshell filling over here. This in here is the D subshell filling, and down here in the lanthanide actinide is the D subshell filling. So we can see then that we're going to be adding the electrons as we move through like that. So in order to write the electron configuration, what we would do is we would write the number of electrons that's in each of those. So the first the first number is going to tell, so here we have 1s2. The 1 is going to stand for the first shell, so that's how many rings away from the center in the Bohr model. The S tells us we're in the S subshell. And then the 2 in the superscript here tells us that there's 2 electrons in here. So we have 2 per each subshell. And then there are the orientations, the X, Y, Z orientations, and those we'll fill into those sequentially. So then as we move over to here, we're going to have the 2s1 is going to be the first new electron over here. So we have an electron in the 1s1, 1s2, and then we now add the next electron in the 2s1. So what we're not showing is we're not showing where the electrons are filling below this outer one. Then this is a 2s2, which would be the outer one here, and so the electrons have paired up. Then we go over to the P. So we have S, P, D, and F, right? So in shell 2 we have the P subshell as well. So we fill the 2p1 electrons. So we have, basically we're showing the filling up in the valence shell. And so we move up, so 2p1, so we have the 2s2 keeps being full, right? And we add another electron to each of the p's. So as we move forward, so we move from the 2s2 up to the 2p6. Now, this is essentially showing you the noble gas configuration. So all of these down here, so for example, we have 6s2, 6p6 for radon. So what this is showing you is that those are the valence electrons. However, the electrons that are in here also have all these other electrons in it filled. So what you can do is you can take the element below that has a full subshell, and you can start your electron configuration from that previous one. So that's how we get the abbreviated notation. So that's called the noble gas configuration. So for example, if we wanted to write the configuration for lithium, we could write it as helium and then 2s1, because it has all the electrons that helium has, and then the 2s1 electron is the new one. So we would report the valence electrons explicitly, so as they're written on this, and then we just put on before it which noble gas came and the shell before, which has the same electrons. So for example, this is showing then how the noble gas configuration is going to look. So for example, sodium is neon and then a 3s1. So if we take a look at our periodic table, sodium is right here, and so we see that the previous noble gas is neon. So it's neon and then adding a 3s1 electron, and that's how we get that noble gas configuration. Similar strategies taken for our calcium and aluminum. Now, it gets a little bit more complicated when we have an ion. So if something's going to be an ion, then that means that a proton or an electron, the counts are not right. Okay, so when you have Na+, that means that in order for it to have a plus charge, it must have lost an electron. So that means it has the number of electrons that sodium has less 1 in order to have a +1 charge. So if we go back and look at our periodic table, here's sodium. So this is how many electrons it has, which is going to be neon +1, and then in order to be Na+, that means that it lost its outer electron. So its electron configuration is actually going to be the same as neon, so we call that isoelectronic with neon. So here also we're going to do similar situations with calcium and aluminum, right? So calcium is calcium 2+, and aluminum is 3+, so we're reporting these as noble gases, so let's see how we got that. So we see that we had calcium, which is right here, and so calcium lost 2 electrons, so we go back 2 places for calcium, and we get that it's argon. And then for aluminum, which is right here, it lost 3 electrons to be Al3+, so we lose 1, 2, 3 electrons, which puts this also back at neon. So that's how the ions go back to their noble gas configurations. Of course, when things are trying to form ions, we're hoping that they would get to the noble gas configuration, because that's the configuration in which they're the most stable. So that's what they're trying to do. So that indeed is why we get these charges as we do here. So then we try to get the noble gas configuration, and that's how they become more stable. So for cations, of course, it's easier to lose a couple of electrons than it is to gain a lot of electrons. So for example, if you're sodium and you have 1 electron and you'd like an octet, it's easier to lose 1 electron than it is to gain 7. So that's why it's going to go to form a positive charge, so it will lose 1 and then it becomes +1. And so similar ideas follow for these. However, as you move to the right on the periodic table, then in that case it's going to be easier to just take up a couple more electrons than to lose so many. So for example, fluorine, which is all the way over here, so fluorine would like to be a noble gas as well, so fluorine could either lose 7 electrons to be like helium, or it could gain 1 electron to be like neon. So gaining 1 electron to be like neon would be much, much simpler. And so here we're showing what the electron configuration is. So this is explicitly, so 1s, 2s, 2p5, so this 2p5 needs to go to 6 so that our outer octet will add up to 8. So if you look here, you see that this one has a superscript of 2, and this one has a superscript of 5 for the ones in the second shell, which we can tell from these 2's here. Then what we see is that we have 7 electrons as we counted on the periodic table, so we need 1 additional electron, which goes right here, and then we'll have the neon configuration, and having the extra electron, it will pick up a -1 charge. Oxygen works in a similar way and needs 1 additional electron than fluorine does. So we have 2p4 is our last entry here, so then to become 2p6, we would need to gain 2 electrons, which is being shown here with the -2, and this 4 has become a 6 to also make it into the neon. Nitrogen, on the other hand, will need to have 3 more electrons, because it's only got 3 and 2 is 5 in its outer shell, so to get up to 8 it will add 3 more, and so then it also becomes isoelectronic with neon. Therefore, because all of these have the neon configuration, these are called isoelectronic. In addition, these are isoelectronic with sodium in the +1 charge, which also has noble gas configuration of neon. So we call those isoelectronic series, as this shows here. So this actually has all of the different series members written out. So here we have neon, so sodium plus is going to have the neon configuration. Al3 plus will be the same as neon F minus. So you see these don't have anything left in their outer shell because they donated them, whereas the acceptors are going to have their outer shell become expanded, that is, it's taking new electrons in the outer shell. So the negatively charged ones are going to be showing additional electrons being added, whereas the cations are going to be empty because they donated the ones in their outer shell. So all of these are going to be isoelectronic with neon. Next, we're going to talk about the shielding effect and the effective nuclear charge, which is Z effective. So as we move down the periodic table, the effective shielding is going to be really easy to understand. So the way this works is that if you have electrons going around the center of an atom, if you have things of the same charge, they're going to repel each other, right? So, for example, if we have a nucleus, and then we come one shell out, and we're going to have some electrons there, the electrons that are in the next shell out are going to be repelled by the electrons that are underneath it, between the outermost electrons and the nucleus. And so you're going to have some of this repulsion here, which is going to cause the electrons then to be not held as tightly in the ones that are further out. So as you add electrons from one shell to the next shell to the next shell out, as you get further and further away, there are going to be more and more electrons between the outer shell and the nucleus to which they're getting attracted, and so they're going to be shielded more and attracted less. So therefore, we're going to have increasing Z effective. However, as we move across the periodic table here, we're going to have another trend, right? So this is trend as we're adding electrons in the same shell, then that's actually not going to be effective very much because there's not really going to be any shielding effect, right? Because you're not adding them in any new shell, but you're adding on additional nuclear charge that's approximately the same distance away. And so the Z effective is actually going to increase as we move across the periodic table in this direction here. So the relationship between electronegativity and the bond type is going to help us to understand the difference between the covalent and the ionic bond character. So we usually talk about ionic and covalent bonds as though they're two distinct separate things, but in fact actually they're not, and it's a continuum of different bond types. So for example, if you have two things that are very positively and negatively charged and they attract, then that's going to be highly polar, and that's going to be an ionic bond, and it's going to have very strong ionic character. But in fact, you're going to have that some things are going to be having covalent, that is when the electronegativities are similar, so that is when they're sharing the electrons approximately the same. So, for example, when we have electronegativity distance in the bonding atoms, right, so when we have a 0 here, then the bond type is going to be covalent, right? Then there's going to be this intermediate ground here where you're going to have the bond type be similar to covalent and similar to ionic, so it's not exactly either one. But as it becomes more ionic in nature, because the electronegativity differences are going to be large, then we're going to have the bond type is going to be much more ionic in nature. So basically, covalent is when the electronegativity differences are negligible, so they are both pulling on the electrons about the same. And then we move into polar covalent, so that's intermediate, and then as the differences in electronegativities become very large, then the bond type is going to be ionic. So as the covalent character is increasing, the ionic character is going to be decreasing because they have opposite ways of operating, right? So let's talk about atomic radii. So when you have something packed in a metal, then we can see that this is going to be modeled by a sphere, and then the distance between the centers of these is going to be based on the size of the sphere. Then when we have things that are going to have the sharing of electrons, then that's going to require that the centers come closer together in order to share the electrons more effectively. Therefore, the radius distance from here to here is going to be smaller than it's going to be, for example, of a similar element which is going to be in a metallic radius. So you see that these circles are cut off, right? So this length is going to be smaller than this length up here. Of course, the same element can't undergo covalent and ionic bonds in the same element, but we're just saying if you could. So comparing between atomic and covalent, the covalent radius is going to have the smaller radius. This is a diagram that summarizes the relative size of some particular atoms. So let's take a look at the trends. So as you add on shells, it's really easy to understand that the more shells you have, the bigger the atom will be. So as we move down the periodic table, you see that cesium, for example, is much larger than lithium or hydrogen. However, the trend going in this direction is going to be a little bit different. So if we have more protons and the electrons are equally close, then the protons are going to pull more easily and they're going to pull the electron cloud in. So effectively, we're saying that the force of the protons is going to be the dominant force here. So as we move over to the right on the periodic table, we have more protons. Having more protons and the electrons being added in the same shell, they're not going to get any more shielding. Not having any more shielding and having more protons, they'll be pulled in more tightly. Therefore, we have this trend that they're smaller on this side and larger on this side. Ionic sizes are going to also have trends, so we just talked about atoms. So for example, the cation is going to lose a whole shell, right? So to become a cation, you're going to lose an electron. So and losing the outer electrons is going to make it become smaller. So it will be smaller than its atom, right? So here's a lithium cation, and when it becomes lithium plus, it's going to actually get considerably smaller. However, the anion is going to gain an electron, and so it's going to get larger because now we have more repulsion of electrons without having any protons to compensate for it. And so therefore we have that the fluorine is going to be quite a bit larger in its ionic form than it is in its atomic form. So here's a picture of the trends in ionic sizes, and so we can see that this trend is borne out. And again, as we move from the top to the bottom of the periodic table, we see that at the bottom of the periodic table, the ions are generally larger than at the top, which makes sense because you have more shells. Alright, so here are the actual values of the radii and picometers of ions of some of the familiar elements, and so again we can see the trends that we have just mentioned. We also need to talk about electron affinity. This is the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous state to form an anion. So for example, here we have some X in the gaseous state and an electron, and it's going to accept this electron. So we're talking about how much does it actually want to take on that other electron. So let's take a look at a real one. Here's fluorine, and here's an electron. Now fluorine is the most electronegative element. Being the most electronegative element, its delta H is going to be very favorable. This is seen by the negative value here, and a large magnitude of 328 kilojoules per mole. So we also can look at the oxygen, and so we see that oxygen also would very much like to take electrons, but its electronegativity is less than that of fluorine. So electron affinities can be looked up on the table. This is the electron affinities of some representative elements and the noble gases. So not surprisingly, the noble gases really don't want to take any more electrons because they already have their perfect configuration. And so we see that at 328, fluorine has the highest electronegativity on the table. We see that many of these over here don't really want electrons anymore because they have very low numbers. And so those are the trends we see. Our highest numbers are over here for the group 7A elements because they need just one more electron, which is not that much, and so it's nearly made its ideal configuration. We also see in general that the electronegativities are going to be higher on the table than they are at the bottom, and this is again because of the lack of the shielding effect for the inner ones, so it will be easier for them to take an electron on, whereas if you're trying to take on one more electron and you already have a whole bunch of them, getting one more electron is not as important than if you just have a few electrons, right? So the contribution to the overall number of electrons is much bigger and has much more of an effect if you have fewer electrons. So electronegativity is going to increase from left to right and from bottom to top. And once again, fluorine is the most electronegative. This is being reported, so these are the Pauling electronegativity values up here, and so they range on the scale from 0 to 4. Again, with fluorine being set at the highest. So, what's the difference between electron affinity and electronegativity? Well, electron affinity is the negative of the enthalpy change when an electron is accepted by an atom in the gaseous state to form an anion. So that's a pretty physical sort of a thing, a very, chemistry sort of a thing. Whereas electronegativity is the ability of an atom to attract an electron towards itself in a chemical bond. So the focus of what they actually mean is slightly different, although they definitely talk about things which are very similar. So electronegativity is oftentimes the one that we use when we're trying to understand the polarity of bonds, which is effectively the reason why the concept of electronegativity was developed, as we want to say, here's some bond, how much do each of the contributing atoms pull the electron cloud, and whichever one is able to pull the electrons towards itself is going to be the one that's more electronegative. So first, ionization energies are going to talk about how much energy is it going to take to remove the first electron. So things which are going to be pretty much perfect and really happy with having their electron configurations are going to be pretty upset about having the first electron taken off. So, for example, here are the noble gases. So if you have the noble gases and they already have their perfect configuration, they're going to be pretty upset about losing an electron. And so we see that these have the highest first ionization energies. On the other hand, these guys over here, the group 1s, are going to be happy to give up an electron because they would like to achieve their noble gas configuration. So in order to achieve their noble gas configuration, they'll be quite happy to give up their electrons. And so these guys have very low values compared to this. So then the trend is that the ones on the left would be happier to give up their electrons, whereas the ones that have the noble gas configuration, as you get closer and closer, are going to be increasingly upset about giving that up and therefore have higher and higher values. We also see again this trend going from the inner to the outer shells of the periodic table, that as we move to further and further shells, the effect becomes diminished, again because of the shielding effect. Because of the shielding effect, there is some similarity in elements as you go on the diagonal on the periodic table. So they are most like the element which they're on top of because of having the same electron configuration, but because of the shielding, there's going to be some differences, and so as we move down the periodic table, then lithium, for example, is diagonally across from magnesium, and so what we're seeing here is that the effect of being, of having the shells to screen the electrons, there's going to be some similarities as we look on the diagonal of the periodic table. So then we are going to look at a variety of elements, and so what we will see in this picture gallery then is that a number of the elements which are in the same column in the periodic table are going to have some similarities. So for example, here we're looking at lithium, sodium, potassium, rubidium, and cesium, and you can see that these have some similar ways of looking alike. Potassium is somewhat unique though. The group 2A elements, here is beryllium, magnesium, calcium, radium, barium, and strontium. We can see that radium is very different than the others, but these all are basically some metallic looking solids. Group 3A elements, this is boron, aluminum, gallium, and indium. So these again look kind of similar. Gallium has the unique property that it has a very low melting temperature, so you can see that it's actually beginning to melt in this person's hand. Group 4A elements. So again, we've got up here the electron configuration. So again, having the same outer electron configuration, we have similar properties. So we got carbon is graphite, carbon is diamond, which have some considerable differences. silicon, germanium, tin, and lead. So these have some similarities in what they're like, of course, except for diamond, which is very unique. And we'll talk about why diamond has such interesting properties. Alright, so group 5A elements. So again, now we're starting to look at things which are looking to have similar interactions. This is liquid nitrogen, so nitrogen's intermolecular interactions are going to be lower than some of its other column mates. Here's white and red phosphorus, so these are two different forms of phosphorus. Here we've got lead, antimony, and bismuth, which again look like solids. And group 6A elements, now we have sulfur, which has this characteristic yellow color and also has a rather pungent odor, and selenium, and this is tellurium. 7, now these are going to be the noble gases, these are going to be the halogens, which are almost noble gases, so all of these want to have one additional electron. We can see that they exist in the gaseous state. So this is iodine, bromine, and chlorine gases, and you can see that they do have a little bit of color in them as well. And then finally in the noble gas we're going to have the gases which are they used to be believed to be unreactive. However, now we know that it is actually possible for them to react. So there are some xenon compounds, so xenon with 4 fluorines attached to it, or 3 oxygens, and so these start to make some very interesting shapes of molecules, which we'll be studying when we look at the molecular orbital theory and the geometries. We'll learn how to name some of these. There's also a few krypton compounds which have been paired, so the idea that noble gases are totally inert is not really true, but in fact they are much, much less reactive than the other elements on the periodic table. So that actually concludes our discussion of the periodic trends. So I hope you enjoyed our chapter, and I will be back soon, and certainly I will be available to discuss any questions or any concerns you have about this chapter when I return. Thank you very much.